We'll finish our discussion of statistics with a look at the normal distribution. In actuality, it's really hard to find a data set with a mean, median, and mode of 0 and a standard deviation of 1. But there are many data sets that do have similar dispersions of the data. This means they still follow the bell-shaped curve, they are symmetric, and the mean, median, and mode are equal. They will still have 68% within one standard deviation, roughly 95% within two standard deviations, and 99.7% within 3 standard deviations of the mean. So anytime people talk about normal distributions, this is what we're looking at, is how is the data distributed within the standard deviations. Luckily, we do not need new charts for each normal distribution. We can convert our data and use the charts from the standard normal distribution. So given a normal distribution with a mean of x bar and a standard deviation of s, we convert the value x to be z equals x minus x bar over s. So let's take some examples to see what this really means. So the average height of an American man is 70 inches with a standard deviation of 4. What percent of men are under 6 feet tall? So first thing I did was say, well, 6 feet is really 72 inches. So to find the answer, I'm first going to start by changing this x is 72 into a z-score. So I take my 72, subtract the mean of 70, and divide by 4 to get 0.5. Be careful when you put this in your calculator. Make sure you're either putting parentheses around the numerator and then dividing by 4, or simplifying 72 minus 70, getting 2, and then divide by 4. Then I look up the 0.5 on my standard normal distribution chart, and you can see it gives me 0.6915. Right. So this says 69.15% of men are under 6 foot tall. So I'm going to stick with this example, but just change the question, and this time I want to know what percent of men are over 6 foot 5 inches tall. Okay. So first up, one more time, is change the 6 foot 5 just into inches. So 6 foot 5 gives me 77. This time I'm looking for over 6 foot 5, which means I'm looking for greater than 77. Greater says read to the right. So remember, anytime we want a distribution where it's to the right of the score I give you, we're going to subtract from 1 at the end. So I take my 77, I subtract 70, divide by 4. 77 minus 70 gives me 7, over 4 is 1.75. So I pull out my chart again, and hopefully you guys have printed out these charts by now so that you have easy access to them as we look through examples. And I look at 1.75, and it says 0.9599. Okay, remember, we're looking to the right, so this is not our answer. We're going to subtract from 1. 1 minus 0.9599 gives me 0.0401, or 4.01%. So let's change the type of example and say, let's look at Espresso. So what if we have a machine that gives a normal distribution of the espresso where the volume is 0.85 ounces and the standard deviation is 0.08. I want to find the percent of time the espressos are between 0.8 and 0.9 ounces. Okay. So notice I gave you two data points, 0.8 and 0.9. That means I'm going to have two conversions. So we will convert 0.8 minus 0.85 over 0.08. and also 0.9 minus 0.85 over 0.08. So I got these two numbers, negative 0.65 and positive 0.65. Remember, when you look at your chart, it only goes to 2 decimal places. So anytime you get more than that, just use regular rounding to change it into 2 decimal places. So I'm changing these negative 0.65 and positive 0.65 just into negative 0.63 and positive 0.63. Alright, so I'm consulting my charts. I can see the positive 0.63 and the negative 0.63, and I circled them both for you. Okay. Anytime I have two values, I'm always going to subtract, and you always put the big number first. So I'm going to put the 0.7357 first, then I'll subtract the 0.2643. That gives me a difference of 0.4894. So this tells me 48.94% of the time the espresso machine will put out a volume between 0.8 and 0.9 ounces. So let's look at another example. Assume that the weight of quarters are normally distributed with a mean of 5.67 grams and a standard deviation of 0.07 grams. If a vending machine will only accept quarters weighing between 5.5 and 5.8 grams, what percent of the time, A, will it accept the coins, and B, will it reject the coins? Okay. So once again, I gave you 2 data points, so we'll do 2 conversions. I'll start with 5.5 minus the mean, 5.67, and then divided by 0.07. And then I'll take the 5.8 minus 5.67 and divide by 0.07. This changes to negative 2.43 and positive 1.86. Okay. Once again, I have 2 data points, so I will look up both of them on the charts. And you can see again, I circled them. So I have 0.9686, and then I have 0.0075. When I subtract them, it gives me 0.9611, which says I have 96.11% of the time the machine will accept the quarters. All right. Flip side of that is easy. If I know that 96.11% of the time the machine is going to accept it, the rest of the times it will reject it. So I don't have to use the charts, no conversions here. I just do 100 minus 96.11 and it says 3.89% of the time the machine will reject the quarters. Okay. So here's an example for you to try. The number of people that ride an amusement park roller coaster is normally distributed with an average of 1,200 passengers per hour and a standard deviation of 300. What percent of the time will there be less than 800 rides per hour? I guess that should really say riders. All right, so give this a try. Make sure you consult the charts and then come back and check with me to see how you did. Okay, so we're looking for x less than 800. We need to convert using the mean of 1,200 and the standard deviation of 300, and it gives me negative 1.33. So on my negative chart, I go over to negative 1.33, and it says 9.18. So only 9.18% of the time would I have less than 800 riders per hour.